Hello, my name is Harald Ackermann. I will present the project Eclipse APP4MC. It's in the track Introduction to the Eclipse ecosystem, so I will shortly describe the technical part and then also describe how we did some demonstrators, some additional things to try to promote our project. I will do the first part of the talk. The second part will do Robert Höttger. We are both committers on the Eclipse APP4MC project, and I'm also the project lead. So, what is APP4MC? No. A short description. So, in a sense, it's a platform that is for engineering of embedded multi and many core systems. So we try to do optimization of these embedded systems with hard real-time capabilities, and the central, as you see here, is a data model, a common data model that we want to use to do exchange between tools, but also exchange between companies who are involved. So both is possible. In this circle you see at the top, for example, some software modeling tools. So you can describe the structure of the software. That is, how is the software activated, how are the calls to other services, how are data exchanges organized. Then we can do some first steps to find parts of the software that are independent, that can run in parallel. We can add some hardware descriptions, some constraints, so things that will guide our optimization process. And then we can do some simulation, optimization, some analysis based on these values. So it's a non-functional thing, it's all regarding timing and scheduling. So what we want to do is we want to have a good placement of software on cores and also on data. So data should be placed in memory, and it should be as good as possible to avoid conflicts and to have a good data access here. Data exchange is shown in this picture. It was part of a report done by one of these OEMs. So they described how they want to have a cooperation model between tier 1 suppliers and the OEM. In reality, it's often the case that the software is done partly by the OEM and partly by the tier 1. And so we have to have a merged model of the overall software. And typically, we are not allowed to see the software of the OEM, and the OEM is not allowed to see the software of Bosch, for example. So we have a high-level description that allows us to deal with it without the details. And as you can see here, the symbol is shown on different places on this graph. So it's used to do all the system design, specification, verification, validation parts. It's often done with simulation because analysis of a dynamic system is often too pessimistic, so worst case execution is not good enough. So then, what is the status of our project currently? So our origin was in two publicly funded projects, ITEA projects. So these are European funded projects, Amalthea and Amalthea for Public. We already did some releases on that level. So we already provided open source with Eclipse public license, but we developed in a closed environment and only published it. And one of the goals of the second project was to really establish an open environment with more participants and more visibility. So we started this project APP4MC as a real Eclipse project, and we still have some other publicly funded projects that help us to also bring this to another context, to new partners and so on. And the dots show we are also providing or try to establish a new project that is now proposed. What you can see here at the top, we now have quarterly releases. So every 3 months we will provide an official release in the Eclipse sense. So it's with release review and downloads and all the necessary formal things. To show you what it means to start a project, I showed the timeline here. So typically you start with a project proposal. You then have this community review phase for a few weeks. And if it is approved, then you are allowed to do the paperwork, as they call it. So you have to sign the committer agreements and so on. And you can do your initial contribution. That means a zip file of all your code you want to provide. Before this, of course, you have to change plugin names, package names, restructure your software. You have to clearly separate own code from libraries you're using. And this is then the main part of this here. So source code is checked and also the libraries are checked, and it took more than a year till we had the full IP review completed. To give you an impression, source code was one issue here. The rest are the used libraries we took. And sometimes it's a lot of work to provide all the used elements because you are not allowed to have nested dependencies. So each and every public library or external library has to be approved. We then set up our infrastructure. So we began with 2 Git repos, one for the code and one for our website. And we set up the build server. So this is also currently done. We started with a Hudson instance and now have a Jenkins instance, as most of other projects are also doing now. So test and automatic creation of products and download sites is done on that level. And we also use the build server to build this page here. If you're interested in more details, this is the best starting point. So org Eclipse APP4MC. And the more detailed and more technical part is always in this project's Eclipse org part. So this is a Drupal instance, so many of the contents are provided automatically, like release reviews and other things. And this is a more generic one where you also see, for example, documentation of our system. Download of complete products is always possible. And yeah, just as a hint, this is done by an offline tool. So we provide the source code in one repo, and then we can start the build process to publish it, and this will also automatically be reflected on our server. The status of the project currently, we have a rather stable number of commits during the month. We have a number also of smaller contributions and also a number of companies who are involved. Bosch has the majority of the commits with about 50%, but also other members are active here. It's not only our work here. What we can do, so not all of these contributions are from committers. So we've also provided a Gerrit instance, I think also a typical one. So if someone wants to contribute, it's a very simple operation. You can clone the repo, and you only have to push to a Gerrit instance. That's another push target. You have to sign the commit, and then it will be one of these entries that have to be processed by one of the committers. So, as you can see, this is a typical situation here. The first verification is done by the build server. If a new commit also builds and the tests are okay, this is the first +1, and then the other parts can be done by the committers. Some formal things, if this contribution is more than 1,000 lines of code and so on, is also handled here. So we tried also to promote our project. One part was dissemination, as it is required for publicly funded projects. So some of these conferences, like the Co-Summit in 2013, are mandatory, so we had to do it, but we did it with some effort and also had a big booth here with a number of participants. We tried to show the project on technical conferences like the Parallel or the Eclipse with very different audiences sometimes. And we also went to fairs like the Embedded World, as you can see here, as part of the Eclipse booth. One thing you saw in the middle was the Waters Challenge. This was an attempt to also include academic research. So we tried to provide a data model, so one example of a Bosch system obfuscated, and this was a challenge to do this formal methods timing verification challenge on this system. So it's one possibility to describe the situation and also to attract others to use this system. One other thing that was complicated or is different for someone who will start to use it, if you have to build models of your software by your own, it's an almost impossible task. So if you already have a software, it's much easier if you can extract some elements from the C code. So it's source code analysis here based on LLVM. And so we can see how are the calls to other functions, accesses to variables, the taking of logs and so on. And together with additional info like how is the activation of specific tasks in all the functions, this is also possible. And in the end, you can build an Amalthea model and can reuse it for visualization, for simulation and other things. So one effect of Amalthea is that some of the companies who provide commercial tools are already importing it. So Timing Architects is one candidate, Incron another one. So you are able to model it once and use several tools to handle your, also to verify the system behavior. The author of that tool is also here in the audience, so if you have any questions. Another thing was more as a side effect. So we had to do model transformation. We wanted to move from one version of the model to another one. And we did do this on the basis of the XML file, so on the DOM model. And to know how elements are structured and where are the possible references to elements, it was a good possibility to have a viewer that shows an ENF model in that sense. You see all the usages of an element or hierarchical structure or the possible relations here. So this was a side effect, a little tool that a colleague of mine did, and this is also open source and can be used with any ENF model. Hope it helps. For us it was a very useful thing. If you're interested, tomorrow there's a 10-minute slot in the modeling symposium where there's a demo of this tool. I will hand over to my colleague.
All right. Thank you very much, Charlotte. Before I start, maybe some things about me. I've been responsible for different multi-core optimization tools within the FMC environment. Basically the partitioning approach that identifies parts of the software that potentially can run in parallel in the system. My colleague is responsible for doing the mapping, so finding an efficient solution how to run these partitions on a given hardware system. In order to validate all our technologies that we have with FOMC, we, as a university, came up with this small, easy-to-use demonstrator. Of course, we validated our approach also, like for example, with the watches model that is provided that we saw recently, in order to check that real industrial applications also are addressed with our technologies. So this demonstrator is also for people that want to get in touch with FOMC and technology, because we try to get this demonstrator as easy and cheap as possible. So it basically runs on a Raspberry Pi. So actually people can just use any Raspberry Pi for it with the standard Raspberry operating system. But we of course have like some sensors, actuators, and some fancy technologies on top of it, of course, as well. So on the right part here on the slide, you see that there's the Raspberry Pi creates a hotspot that any computer can connect to, and you open a website that is generated on the Raspberry, and it looks like this. So you can more or less control the rover, so steer it in different directions. You can see the core utilization, and you can also see some sensor values. We also have some rudimentary cruise control and accelerated cruise control implementations just to stress the Raspberry Pi a little more. And there's also an image processing we implemented, so a camera that you see here, Conrad, just to stress the Raspberry Pi and check if the real-time things are still there when there's much load to be computed. Of course, this is very rudimentary, and since the Raspberry Pi is not an embedded system platform, however, we kind of combined this with different technologies like tracing in order to get an impression of the real-time values as much as possible. We also have lots of documentation, and we have a Git repository also that is accessible to the public, where there are basically two documentation. One is about setting up the whole website generation and processing. However, we also provide ready-to-use images, so you can just directly apply the image to your SD card and run the application directly. You can also do everything from scratch, and it's described in the documentation. And the second documentation describes things about tracing. So actually we use some Linux tools for that. Precisely, we use perf tooling to record traces during the system execution. We convert those perf traces to CTF with a library called libbubble_trace. And the CTF traces can be imported into Eclipse Trace Compass, for example, and there you can see the execution of your program on Raspberry Pi with the Gantt charts and the CPU utilization and so on. This is a small overview, because what we also did with all the implementations that we did, of course by hand with the C++ files and so on, we modeled the system with FOMC. So we got all these models for the software, for the hardware, and with these models we perform, of course, our partitioning mapping technologies, and these information are used at the Raspberry to pin or to map the tasks that are generated to cores, to one of the 4 cores on the Raspberry. However, the rover is still under progress, so in a new project we also use more IoT technologies and cloud technologies, and currently we have 3 or 4 rovers across some partners, but we're about to order 20 more of them for all of the partners involved, and we also want to get, because we developed everything from scratch, we want to provide soon some ready-to-use package so that you can order the rover directly. And you can see here, like the black part is a 3D printed model. And since not everyone has a 3D printer, of course, we want to provide this as a complete package. Now the next slide shows how we modeled this. So eventually we did this by hand, the modeling, but with the new tooling that Harald mentioned earlier, is we can use the C to Amathere conversion process in order to generate at least the software model on the left part automatically. And here you can see like different tasks, labels. They are kind of just memory accesses to the memory. And like on this part here in the background, you see the hardware model with the different cores, the frequency, and the memory. From there, in FRMC, you can use the multicore wizard that guides you through all the different processes and guides you also through the configuration steps, because there are a lot of different configurations in order to constrain and adapt towards some constraints and user-specific needs. And then enhanced model is generated that contains not only the runnables, but also the so-called process prototypes that are just preliminary tasks. So afterwards, the tasks are generated, and from there, when the mapping is performed automatically, you get this allocation where if you use this allocation on your system, then the deadlines are not missed, or if they are missed, then of course the user gets information about that, and so that load is balanced depending on the different optimization goals that you can configure during the multicore wizard configuration process. Now for the rover, we also have some rudimentary code generation, and it basically just generates one C++ file where a library is used in order to perform this static mapping of the different task cores. All right. The rover is also, I brought it with me. I don't have it here right now today because we have limited time. However, tomorrow there's the IoT playground here from, I think, midday till evening. And I'll be at the IoT playground booth and present the rover. So if you're more interested in that and what kind of technologies we use precisely, then I can introduce you to those technologies by then. This is also something that comes with the FRMC for free, of course. It's a rudimentary simulation, and you can also adapt the simulation, of course, because we provide an API for that. And here you see the different 4 cores and the executing of a task, the idle times of a task, the waiting times of a task, and deadline misses if there are some. Yeah, this is just something that I mentioned earlier as well with the trace compass. Here you have a bigger screenshot, and you can see how your system was actually executing. We also have we made some experiments where we compared our distribution with the operating system distributions and sequential distribution. Sequential is of course no distribution at all, but at least compared it to sequential execution. And in some cases we were also able to outperform the dynamic scheduling of the operating system. And this is some kind of extension to what Hannah mentioned earlier. So we of course published a couple of papers, and also we're happy to receive some best paper awards. And on the Amathere for Public project that ended in August, we had 31 scientific publications at some conferences, and we also participated at the Digital Innovation Forum, Orica Innovation Week, and the Embedded World CeBIT Co-Summit. And different Eclipse cons. Also, what we were quite happy about is in Dortmund we were able to have this Google Sum of Code project with the student together. So it has synergies with the rover, but it's not a rover, it's an RC car. So it drives a little bit faster, it has a different steering mechanism, and it actually has more computation power because there we have distributed systems, not only the Raspberry Pi, but also a real-time board. So actually it's an XMOS controller with 16 cores, so we had a little bit more flexibility according to distributing the software. And also like defining the constraints such that a very critical steering task, for example, runs on the real-time board and gets a dedicated core, for example, in order to have the execution times without much interruption. And also, like, the GSOC project lasts about 6 months, and it ended this month. And all the code, according to their C card, is also available along with the Google Summer of Codes projects. So it's called A4M car, and you will, if you just Google it, you should find it, of course. Here are some Git repositories for the different technologies. We also, for the RC card that you see here, that was our first version, that was our second version. It also features a display, so you can actually, on demand, kill some processes, start some processes, and also online change the distribution, at least for the Raspberry Pi. In order to change the distribution on the other XMOS board, we need another flash, or we can do that online. And you can switch through different distribution scenarios and then see also like the core utilization on the display directly. We also have a small Bluetooth app. So on an Android phone, for example, to steer it, but of course you can also steer it from the website. All right, I have some minutes left. So this is something that we're investigating right now. It's very recent developments. They're not directly related to FMC, but related to another publicly funded project called AppStackle. And there, as I mentioned earlier, we go a little bit more into the clouds and connectivity aspects. So what we do there is we use Eclipse Hono instance running on our servers, and we send data from the rover to this Hono instance and can currently just visualize these data. So on top you see the core utilization. It's not very clear, but I hope you can get an impression. You see here the front ultrasonic sensor values, the rear ultrasonic sensor values, and the 4 infrared sensor values. They're directing into 45-degree angles to the front left, front right, rear left, and rear right. And also all bearing information. Of course, this is therefore the rover requires internet connection, and I'll provide all these, also like the live views of the sensor data at the IoT Playground tomorrow. And yeah, we recently adapted also the OLED display on the rover itself to get some information about the Wi-Fi, Bluetooth, Hono connection, things like that. We also have a small buzzer, and we're planning to do a hackathon in February next year to extend like the use of the rover across the community. And these are some outlooks that we have. The green ones are things that we already did. The blue ones are things that we're approaching in the next months, years, at least within the project. So we already did this Hono instance, and we're currently investigating how to use Eclipse Hawkbit in order to apply over-the-air updates to the rover, but of course to any arbitrary hardware as well. On the rover, we want to use AGL, automotive grade Linux, in order to apply to platform-specific developments that are related to the automotive domain. And we want to use the gray part is like more the intention, and the white part is the technology. So Eclipse KT for security, Capua for device management, Mosquito for MQTT protocols, and Eclipse Vision for lightweight M2M management, and Dito for digital twins, and this brand new Eclipse Duo for having traffic simulation, for example, running in the cloud, and then calculating how the rover can react to simulation traffic. So that is something that we currently do not do, but we want to do. So also transmitting data from the cloud back to the rover, so bidirectionally. Something AppSec also addresses is like over-the-air upgrades in order to have some applications running over the rover that can be changed from a remote server. All right, I think we have some minutes left for questions. So far, thank you very much for your attention. So, are there any questions left? Last slide is not working somehow.
Okay. Just kidding. Don't use us, please vote.
There we go. No questions? Of course, if you want to know more about the technology itself, please let me know. There are also some papers in this regard, but I can tell you all about what constraints we consider, how we try to achieve the best worst case execution time and so on. Or just simply drop by tomorrow. Would be great.